Here the argmin channel, real analysis video series, lecture 27 on the completeness of a function space and the ICT integral convergence theorem. So we looked at, I introduced the convergence theorem, the completeness theorem, sorry. And here's the statement. If K is a subset of Rn and it's compact, then the continuous functions mapping K to Rm equipped with the uniform norm is a Banach space, i.e. it's a complete norm vector space. So let's prove it. So let's start by assuming everything in the hypothesis. So assume that is compact and let Fk be a Cauchy sequence in the space of continuous functions from K to Rm. So write that as CKRM. Now let epsilon greater than 0 be given. Since it's a Cauchy sequence, there must be a natural number big N such that Fk minus F L, because it's Cauchy, less than, we'll figure this out later, for all K, L greater than or equal to N. And for each point X in the domain K, for KL greater than or equal to N, it must be that Fkx. So now this is a number or a vector in Rm, and F Lx, so this is the normal 2 norm, is less than or equal to Fk minus Fl, the infinity norm, because the infinity norm is a supremum, so it's the largest difference, and that is less than, let's fill this in later as well, because that's going to be dependent on that last one. So that's this right hand side is the left hand side of this, so it'll be less than the same thing. Hence, for each X in K, the sequence of Kx is Cauchy. Since Rm is complete, each Fk of X must converge to some Y depending on the X, so Yx in Rm. Because of completeness, so Cauchy sequences must converge inside of the set they're in. Rm is complete, so that Cauchy sequence must converge to Rm. Now let's define F such that it maps K to Rm by F of X is this real number, or this real vector in Ym, Y sub X. Claim Fk converges to F uniformly. By the way we constructed it, each, since it, for every x, it converges to y sub x, so this fk goes to f, since the f is just y sub x pointwise. So that just means the limit as k goes to infinity of fk is f. Now we're going to show its uniform convergence. Suppose k is larger than n, and the n we defined up there at the top. Then if you take fk minus f, that is going to be the limit as m goes to infinity of fk minus f m, which is, each of them are going to be less than epsilon over 2. And let's just fill that in now, because I don't think we'll need to do any trickery later. And that is less than epsilon. So fk converges to f uniformly. And now we just need to show that this f is in the original space of the continuous functions from k to Rm, since each fk is in C KRM, and these fk's converge to f uniformly. Then f is also continuous by the theorem we showed last class. So that's it. And it's continuous over the same domain as fk, so that's why it's in ck. So that's why it's in the continuous functions from k to Rm. Okay. Now let's look at some integral stuff. So the uniform convergence of integration. This is called the integral convergence theorem. If we have a sequence of functions that are continuous and have domain A, B, and implicitly this means that it has range R or codomain R, so it's a real valued function, then if we define fn x is equal to the integral from a to x of fn of the dummy variable t, then the sequence of functions converge to f more importantly converge uniformly to this big F of x is equal to a to x of ft dt. if fk converges to f uniformly. So we're looking for the convergence of this, of a sequence generated by this rule, where each big F of nx is defined by this integral dependent on the small f of n. Proving it, let's suppose fk goes to f uniformly. Now, as part of the proof, claim that fk converges to f uniformly, where these big F's are defined above. So let epsilon greater than 0 be given. So there is a n in this such that fk minus f, the norm, is less than, I'll write down epsilon for now, but that might change later, for any k greater than or equal to n. Then suppose that k is greater than or equal to n, then I'll just indent this so this is still proving the claim. If we look at fk minus f, we're going to want to show that it is uniform. We're just substituting definition, and then substituting the definition of the big F's. So a x fk t d of t minus ax ft dt since the limits of integration are the same and the integration variable is the same, we can just combine them. K of t minus f t dt and if we have there's a property of integrals, it's similar to the triangle inequality where you can move the absolute value inside. Minus f t dt, and this is just the same as or it's going to be not the same, it's going to be less than. Okay, that's what I wrote. I'm writing faster than I'm thinking. Then the supremum inside, or the largest difference, or we just write the infinity norm. dt, and this is just equal to supremum of x and x minus a fk minus f infinity, because this is just a constant with respect to t, so the integration looks like that, and this is equal then to b minus a times this infinity norm, and it's less than b minus a epsilon from the inequality right there at the top, and if we divide that by b minus a, since that's a positive, that still holds, so then this becomes b minus a equal to epsilon. So we have uniform convergence of that integral. And one little remark, if fk converges to f uniformly, that means that fk goes to f and fk of b would go to f of b. So if you do this, a b fkt dt, so you're integrating from the endpoints of the input interval. Remember, these f's are from a to b, that closed interval. Then that is just going to be equal to f of t dt plus ab, this limit. Okay, and that's it for this lecture.